The speaker again. Our next speaker is Anqi Wu, who will be presenting the paper Deterministic Variational Inference for Robust Bayesian Neural Networks.
Hello, everyone. My name is Anqi Wu. Today, I'm excited to talk about this work on deterministic variational inference for a robust Bayesian neural network. First, let me briefly talk about why we care about Bayesian neural network. Here is a standard neural network. A standard neural network is popular and well known for covering a flexible class of models. But the weights in a standard neural network are deterministic parameters which can be optimized via backpropagation. However, in a Bayesian neural network, the weights are treated as random variables with priors. Therefore, this enables a Bayesian neural network to not only provide a flexible class of models, but also provide a principled handling of uncertainty and regularization over the weight. Okay, so the goal of Bayesian neural network is to estimate the posterior distribution over the weight W given the input X and output W and output Y. However, it is usually not possible to write down this posterior distribution in closed form expression. So a general solution would be variational Bayes. Variational Bayes uses a variational approximate posterior Q of W parameterized by theta to approximate the true posterior. And the method maximizes this well-known elbow with respect to the variational parameter theta. The elbow objective function consists of two terms. The first term is the expectation of the log likelihood, and this term is used to fit the data. The second term is the Kel divergence term, which prevents the Q distribution from straying far away from the prior, and this term functions as a regularization term. However, in practice, maximizing this elbow doesn't really work that well. There are mainly two challenges with respect to these two terms that people have to solve. And in this talk, I'm going to explain these two challenges and show how we successfully solve these two challenges. Okay? So let's talk about the first challenge. The first challenge is with respect to the expectation term. This expectation term is usually not possible like being written as a closed form expression. So people use Monte Carlo-based method to approximate this expectation using samples. However, sampling-based method usually results in non-negligible gradient variance during stochastic inference. Here I show the plot between the number of samples used in Monte Carlo approximation with respect and with the gradient variance. We can see when we have a small number of samples, the gradient variance is pretty large. And although we have a large number of samples, the variance is not zero. Large gradient variance could harm the stochastic inference procedure. Therefore, methods have been proposed to reduce such gradient variance for a Monte Carlo-based method. Our method is quite different from theirs. We want to propose such a deterministic approximation method instead of Monte Carlo-based method. Therefore, there's going to be no gradient variance at all. Okay, how we do it? So let's first take a look at the process for Monte Carlo approximation for elbow. Suppose we have such a multi-layer neural network. In order to get the expectation, we need to do sampling. So at the beginning, we sample W from the distribution in the first layer, and we multiply samples of W with the deterministic input X to get the samples for the first activation layer for A0. We can do the same sampling for the second for the second layer, and then we can get the samples for the second activation layer, A1. And we can repeat the same procedure all the way down to the output layer to get samples for AL. Now we can calculate the expectation term using these samples AL for the output layer. Okay? So we just show that how Monte Carlo method propagates uncertainties via samples. Our method wants to deterministically propagate distributions of W instead of samples to the output layer. what we can do is, given a single neural network layer, we propose this function. And this function takes the distribution of the input layer and the distribution of the weight as the input arguments and output the distribution for the output layer A1. Notice that this output distribution A1 has to be Gaussian. The reason is that we know A1 is a linear multiplication between the weight W and hidden layer H. Assume W and H are both IID samples, and there is a large number of hidden nodes in H. According to central limit theorem, this distribution of A1 can be approximately Gaussian. So here is a simple illustrative example for this central limit theorem for a two-dimensional A1. Suppose W is from a two-dimensional Gaussian and H is from a truncated Gaussian. If we have only one hidden node, this will be the distribution of A1. But if we keep increasing the hidden size D up to, say, 100, now A1 looks pretty like a 2D Gaussian. So this is saying, using central limit theorem, we can approximate the distribution of A1 with closed-form Gaussian. The only thing we need to calculate is the mean and the covariance of this Gaussian distribution. This calculation is actually mathematically non-trivial. We have to come up with some approximation method to solve this problem. I'm not going to go much detail here for this mathematical derivation, but the only thing I want to emphasize is, in practice, the calculation of the mean and covariance for this distribution can be approximated using few lines of code without any for loop. So this is very efficient. Okay, I just showed that how we can propagate distributions instead of samples. Here I show the empirical verification to show how well our deterministic approximation can can approximate the histogram of the samples for a neural network. The left is a two-layer neural network, and the right is the model fit. The red dots are the data samples. The output of the neural network consists of two nodes. The first node is M node, which is used to model the mean fit, and the second, which is this solid blue curve in the model fit figure, and the L nodes capture the uncertainty of the model fit, which is indicated by the light blue region. So if we before training, we can sample M and L from model priors, and we can get this histogram of the samples, which are these blue bars. We can also use our deterministic method to fit a Gaussian shape, which is these red curves, on top of the histogram, and we can see they match each other pretty well. After training, we can also, our deterministic method can also fit the histogram of M and L pretty well with a Gaussian bump. And these M and L are samples from posterior distribution. So this is saying, using our deterministic method at any stage of the training procedure, our method can well capture the Gaussian distribution that approximately generate these samples of the output layer in a neural network. Okay, so far I've just shown that how we can solve the first challenge with respect to the gradient variance. And next, let's talk about this KL divergence term. The second challenge is what we call a prior tuning in the KL divergence term. How effectively we can select an appropriate prior for P of W so that the fit is neither underfitting nor overfitting is always a critical issue to solve. Here I show why it's critical. We apply a Bayesian neural network with using variational inference to 9 different UCI regression data sets. Each subfigure is one data set. The x-axis is different choice of prior variance. The y-axis is the test log likelihood. The higher, the better. And we can see the likelihoods are not that consistent across different choices of prior variance. They're pretty sensitive. So a general solution would be cross-validation. But here we want to use empirical Bayes method to automatically select the optimal prior variance instead of using cross-validation. Here is how we do it. We have this Gaussian prior over the weight W, and the Gaussian prior has a zero mean and prior variance S. We also put a prior over S, which is usually this inverse gamma distribution with shape alpha and scale beta. Instead of doing sampling as a general, like fully Bayesian framework would do, we choose to maximize the elbow with respect to the prior variance S. Due to the inverse gamma prior and the conjugacy, the optimal value of S can be written down as a closed form function of the variational parameter theta. And then we bring this S star expression back to elbow, we can derive this empirical base elbow. Maximizing this elbow with respect to the variational parameter only, we will implicitly optimize prime variance S when theta changes. Okay? Notice that we can either set one single prior variance over the entire neural network, or we can set different prior variance S for different layers. So here I show this empirical verification for empirical base. The blue line is the empirical base when we set S for different layers. Applying the method to the same regression data sets and same regression model, we can see empirical base outperformed the fixed prior variance model for almost all the data sets. So this is very effective. Okay, so far I've just shown that we successfully solved these two challenges with respect to the two terms in elbow using deterministic variational inference and empirical base. Here, we show this quantitative comparison between empirical base and fixed prior, as well as deterministic and multicolor variational inference. We can see deterministic variational inference plus empirical base outperforms the other methods for almost all the data sets. So in conclusion, in this work, we propose a deterministic approximation method for the elbow, which eliminates gradient variance usually occurring in sampling-based method. We also provide this empirical-based method for prior tuning issue, which requires much less tuning for the prior. And these two methods together can make the Bayesian neural network with variational base much more stable and robust. Moreover, in practice, the approximations in our algorithm can be well implemented and very efficiently by just calling a few spatial functions. So the code has been implemented in TensorFlow, and independent implementation in Tensor2Tensor is also available by Google. So welcome to our poster, and thanks for all my collaborators, and thanks for listening. Thank you very much.
We have time for one quick question.
Hi, great talk. So I just wanted to clarify this approximate posterior over the activations. Do you assume, is it an isotropic Gaussian, or do you also model the covariance across activations of hidden units?
Yeah, we do, we do model heterostochastic variance for Gaussian instead of actual homostochastic. So we model both the mean and the covariance for each hidden layer and each activation layer for the neural network.
Sorry, I didn't understand the response. Do you model it as a covariance matrix or just a diagonal matrix, full covariance or diagonal?
So for each layer, we model the full covariance, but we also have diagonal approximation for that to improve the computational efficiency. Welcome to come to our poster, and I'll explain that part.
Thanks.
Yeah.
Let's thank the speaker again.